Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 111, minimum depth of a binary tree. Given a binary tree, find its minimum depth. The minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node. Note, a leaf node is a node with no children. So let's look at this binary tree. What are the leaf nodes? Well, it's going to be this 9, this 15, and this 7. So essentially, we're asked to find the leaf node at the shortest path from the root to the leaf node. So basically, the leaf node that is highest up in the tree. So if, our root is technically at level 1, then everything on this level will be level 2, and everything on this level will be level 3. So as we can see, the leaf node that is closest to the top is going to be this 9, right? So how do we actually want to do this? Well, what we want to do is we obviously want to start from the root, and we want to explore all the root to leaf paths and basically figure out at which depth each leaf occurs at, and then we can simply return the minimum of those paths. And that's all we want to do. We just want to kick off a depth first search from the root, go to all the leaves, and when we hit a leaf, basically update some variable which is going to track whether or not it's going to track what the minimum depth we've seen is, and if we see a depth less than whatever our current minimum is, then we can simply update it. Once the DFS ends and explores all paths, we just return whatever the minimum was, and there you go, we are done. So pretty straightforward. This is an easy level question, nothing really crazy here. This is just going to test your basic knowledge of how to actually traverse a binary tree, and that's really all that's doing. So let's go to the code editor and write this up because it's really, really simple. So I'll see you there. We're in the code editor and it's time to write the code. One thing that we want to watch out for is in the constraints of this problem, we're told that the number of nodes in the tree can actually be 0. So in this case, if we're given basically an empty root, which is that case where there's 0 nodes in the tree, then we should just return 0 because technically there is no tree and therefore there is no depth to our tree, so we just return 0. So we're going to say if not root, so basically if we're given a null node, we want to return 0. Otherwise, what we want to do is we want to set up a variable to keep track of our minimum depth. So we're going to say self.minDepth is going to equal to float infinity, and what we're going to want to do now is, remember, we need to basically go find all the root to leaf paths in the tree and then figure out the depth at which we see that leaf. So we're going to say self.dfs, we're going to pass in the root, and we're going to pass in 0. And what 0 represents is the current depth that we're at. So before we start, we're technically at depth 0, and then when we process the root, we'll be at depth 1, right? So what we're going to do, let's now, at the end of our DFS, we can simply return self.minDepth. And then what we want to do is actually define this DFS function. So we're going to say def DFS, we're going to take the node and we're going to take the current depth. And if our node is empty, then we simply want to end our recursion. We have either hit a leaf and we tried to go into its left or right child, but nothing's going to happen. Or we simply, some node didn't have a left or a right child, so we went down a path we shouldn't have. So we're going to say if not node, then we simply just want to return, break the recursion, and get out of there because that path is fully explored. Otherwise, we could be at a leaf node. So in this case, we actually need to check whether or not our current depth is actually smaller than our minimum depth. So we're going to say if not node.left and not node.right, because remember, a leaf is a node with no children. So if it doesn't have a left and a right child, therefore it is a leaf. What we want to do is we want to say self.minDepth is going to equal to the minimum of whatever our current best answer is, and whatever the current depth is plus 1. And we actually haven't taken into account the current plus 1 from the previous level, so that's why we add it here. For example, obviously we start our DFS at 0, then we get to the root, this is 1. When we get to the 9, when we call into the 9, this will actually be called with the node 9 and cur depth of 1. But if we just return the current depth, it would be off by 1. So we need to increment the current depth by 1 when we're doing this check here. Otherwise, our answer will be off because we haven't accounted for the fact that we're at this level. Otherwise, what we want to do is simply go into the left and we want to go into the right, and we're going to increment our depth by 1 because we're now going to the next level. So we're going to say self.dfs node.left, and we're going to say cur depth plus 1, and then we're going to say self.dfs node.right and cur depth plus 1. So let's just make sure we haven't made any syntax errors. Cool. And let's submit this, and it works. Cool. So what is your time and space complexity for this algorithm? Well, we know that we have to explore every single path in our tree to find basically all the root to leaf paths in the tree, which means that we're going to have to visit every single node, and that's going to cost us big O of n time, where n is the number of nodes in our tree. What is the space complexity? Well, we're doing this in a depth first search manner, and we're doing it recursively. So even though we're not creating any data structures to actually perform the recursion, because recursion implicitly has a stack frame requirement when we call, a function recursively, we can think of this as having big O of n space, where again, n is the number of nodes in the tree. And this is going to occur in the worst case where we have a tree that's completely slanted. So just think of like only left children or only right children. Then our stack is going to have to hold the entire tree. So that is why it's big O of n. So if we count stack frames, otherwise big O of 1, because we don't define any data structures. So some interviewers will be like, that's fine, you don't have to count the stack frames, count it as constant space. Some of them will actually want you to account for the recursion. The best answer in this situation is always to say it's big O of n if we count the stack frames, otherwise it's big O of 1. This shows that you understand that you aren't defining any data structures, so technically it's big O of 1, but that recursion comes with a cost, and you have big O of n from those stack frames. This will just show a deeper understanding, and that you're also just thinking about more than just the solution to the problem. So this is going to be a really good code signal for your interviewer. Anyway, that is how you solve this problem. I think it's a little bit trickier than an easy, because it's kind of easy to mess this one up if you don't know what you're doing, but luckily you have this video and now you know how to solve this question. If you enjoyed this video, please leave a like and a comment. It really helps with the YouTube algorithm. If you want to see more content like this, please subscribe to the channel. I have a ton of videos and I have more on the way, so it will help a lot with your Leetcode preparation for those on-site interviews. Otherwise, thank you so much for watching this video and have a great rest of your day.